Chapter 7, Similarity. Section 1, Ratios and Proportions. So similar shapes have the same angle measures, so the angle measures are all congruent to the corresponding angles in the other triangle. And the dimensions are in proportion to each other. So we've proved triangles congruent before. In this chapter, we're going to focus on proving them similar, meaning that they have corresponding angles are congruent and corresponding sides are in proportion. So here you can see I have two equilateral triangles, so obviously all of the measures are 60 degrees, but obviously the sides of the triangles are different. We're going to talk about a little bit more in the future that the triangle has been dilated. So in this case, the triangle has dilated by a certain scale factor, and we'll get to that in the future. It is possible to have corresponding angles congruent. So in other words, all the angles aren't congruent to each other, but corresponding angles are congruent. But in similar triangles, so these two triangles will be similar, and we're going to show that in a second. In similar triangles, the corresponding angles are congruent and corresponding sides are in proportion. Now this question is asking, are the triangles similar? Well, in order to find out if the triangles are similar, you have to see if they have a scale factor. So the corresponding sides would be the 2-inch side to the 3-inch side, the 5-inch side to the 7.5-inch side, and the 6-inch side to the 9-inch side. You want to see if there's a scale factor that gets you from one triangle to the other. The easiest way to do this is just, for this circumstance, to reduce the fractions. Well, 2/3 is already reduced, 6/9 reduces down to 2/3 as well, and 5/7.5 is also going to reduce down to 2/3. Since all corresponding sides reduce down to the same ratio, that's going to be the scale factor, or the between the two triangles. So we have the following triangles are similar, so we were being told that they are similar, and it's asking to find the length of the missing side. Well, in order to do that, we're just going to set up a proportion. Corresponding sides are in proportion to each other since they're similar. So 4/1.5 has to be equal to 8/x. The sides are in proportion to each other. You can also write this as 1.5/4 is equal to x/8. We could also do 8/4 is equal to x/1.5, or 4/8 is equal to 1.5/x. So you can see in this first circumstance, the base of the big over the base of the small equals the side of the big over the side of the small. Here I just took the reciprocal, so I started with the small triangle first in the numerator for both ratios. In the next example, 8/4, the side over the base of the big triangle equals the side over the base in the small triangle. And then here again, I just took the reciprocals of both ratios. These are all the different possible ways you can solve it. When you set it up, there just has to be a relation for the ratio and then the proportions to work when you set them equal to each other. Either way, no matter which one we start with, let's say 4/1.5 equals 8/x. It is a proportion, so we're going to cross multiply. So we get that 4x equals 12. Divide both sides by 4. That means that x equals 3. So 3 inches is the length of that missing side. So here we can just review the actual terminology used for proportions and ratios. Proportion is an equation that states that two ratios are equal. So we have A/B and C/D. This is a ratio, this is a ratio, they're equal to each other. What's circled in red is called the means, and what's circled in blue is called the extremes. Now this is just a different way of writing it. A:(B) equals C:(D). Still the same thing, but instead of writing it as fractions, we have it written using a semicolon. The means are the inners and the extremes are the outers when you write it this way. So in a proportion, the product of the means equals the product of the extremes. That's why we can cross multiply and solve.